Welcome! In this video we study the injectivity of linear transformations. The concept of injectivity is not limited to linear algebra. In general, a function f from a set x to a set y is called injective if for each element y in set y, the equation fx equal to y has at most one solution x in set x. As an example, consider the function from the real numbers to the real numbers given by fx equal to e to the power x. Let's look at the solutions of the equation e to the power x equal to y. If y is positive, this equation has precisely one solution, namely x equal to the natural logarithm of y. If y is smaller than or equal to 0, the equation has no solutions. We conclude that for each y in R, the equation has at most one solution. So indeed, this function is injective. Now let's look at a counterexample. The function f from the real numbers to the real numbers given by fx equal to x squared. Let's look at the equation x squared equals y. If y is positive, this equation has two solutions, the square root of y and minus the square root of y. This means that the function fx equal to x squared is not injective. How does this work for linear transformations? The definition can be translated easily. If t is a linear transformation from Rn to Rm, then we say that t is injective if for every y in Rm, the equation tx equal to y has at most one solution x in Rn. What is special about linear transformations is that we can tell whether it is injective or not from the properties of the standard matrix. Suppose T is a linear transformation with standard matrix A, then the following statements are equivalent. T is injective and A has a pivot position in each column. We know how to find pivot positions. Row reduce the matrix to echelon form. It is very special for linear transformations that there is a general procedure to determine injectivity. To illustrate why this theorem is true, let me show you two examples. First, consider the matrix transformation T from R3 to R4 with this standard matrix. Is T injective? By definition, this question comes down to the following. Does the equation tx equal to y have at most one solution for each y in R4? The equation tx equal to y is the same as the equation a times x equal to y. Let's look at the augmented matrix of this equation. If you apply row reduction, you find the following reduced echelon form. The stars on the right are elements that depend on the components of vector y. You can calculate them if you want, but the precise dependence is not important here. For the number of solutions, only the last element matters. If it is non-zero, the system is inconsistent, so in that case there are no solutions. If it is equal to 0, the system is consistent. Here comes the point. There is a pivot position in every column of matrix A, so the equation has no free variables. That means that it has precisely one solution. So for any vector y, the equation ax equal to y has at most one solution. We find that T is injective. You see here how injectivity follows from the fact that A has a pivot position in every column. It means that there cannot be free variables in the equation ax equal to y, so there is at most one solution. Let's look at a slightly different example. Is this transformation injective? Again, the question is, does the equation ax equals y have at most one solution for each y in R4? Let's look at the augmented matrix that corresponds to this equation. As you can check, it can be row reduced to this reduced echelon form. Again, the stars on the right depend on y1 to y4. The precise form does not matter. What is important is the following. If these two elements are 0, then the equation is consistent. This can happen, for example, if y is equal to the 0 vector. Since matrix A has only two pivot positions, there is a pivot-free column. That means that the equation has a free variable, and hence that there are infinitely many solutions. So there are choices of y possible for which the equation ax equal to y has more than one solution. We conclude that T is not injective. These two examples illustrate the theorem that I showed you before. You can tell whether a linear transformation is injective or not from the pivot positions of the standard matrix. Pivot positions are related to other properties of a matrix as well, such as invertibility. Therefore, injectivity of a linear transformation is related to other properties of the standard matrix too. You will learn more about such relations in the rest of the section.